Imagine a city that rises into the sky and drills deep into the earth powered by the planet itself. Urban sprawl is no longer sustainable. But what if millions could live, work, and thrive vertically without destroying green space or exhausting resources? Today on Civil Engineering Edge, we uncover the engineering secrets behind vertical cities where geothermal power fuels skyscrapers and underground networks create a self-sustaining urban future. Welcome to Civil Engineering Edge, the channel where advanced engineering knowledge meets the future of infrastructure, urban planning, and sustainable development. As civil engineers and future city designers, we are witnessing a historic shift in how cities must be planned and built. Rapid urbanization, climate change, land scarcity, and rising energy demands are pushing traditional city models to their limits. Horizontal urban expansion, commonly known as urban sprawl, has proven inefficient, resource-intensive, and environmentally destructive. The challenge before us is not simply to build taller structures, but to reimagine cities as vertically integrated engineering systems. In this video, we explore the concept of engineering vertical cities' urban environments that grow both upward and downward, powered by geothermal energy and supported by advanced underground infrastructure networks. These cities are designed to house dense populations within a minimal land footprint while maximizing energy efficiency, resilience, and sustainability. We will examine how geothermal systems can be integrated into deep foundations to provide continuous heating, cooling, and power to skyscrapers. We will also explore subterranean transportation systems, utility tunnels, energy storage zones, and service corridors that allow cities to function efficiently below ground. This topic sits at the intersection of structural engineering, geotechnical engineering, energy systems, and urban design. If you are a civil engineer, a student, or an infrastructure professional, this video will give you a clear technical vision of how future metropolises will be engineered not outward, but vertically and intelligently. The vertical city unveiled. Why we need them now. Modern cities are facing unprecedented pressure from population growth, climate change, infrastructure overload, and land scarcity. Traditional urban development models based on horizontal expansion are no longer capable of supporting future demands. This is where the concept of the vertical city becomes essential. A vertical city is a three-dimensional urban system where residential, commercial, institutional, and infrastructural elements are integrated within a compact footprint. Instead of spreading outward, cities grow upward and downward, optimizing land use and reducing environmental impact. From a civil engineering perspective, vertical cities require advanced structural systems capable of handling extreme vertical loads, lateral forces, and long-term serviceability. Deep foundations, high-strength materials, and intelligent load transfer mechanisms form the backbone of these developments. However, the true value of vertical cities lies beyond structural height. These cities are designed as integrated systems where energy, water supply, drainage, transportation, waste management, and communication networks function cohesively. This integration significantly improves efficiency and resilience. Vertical development also enables surface-level land preservation for green spaces, flood control zones, and ecological restoration critical for climate adaptation. As urban challenges intensify, civil engineers must move beyond conventional design approaches. Vertical cities represent a necessary evolution in urban engineering, offering sustainable, resilient, and space-efficient solutions for the cities of tomorrow. The impending urban crisis. Why current growth models are unsustainable by 2050. By 2050, more than 70% of the global population is expected to live in urban areas. Current urban growth models, dominated by horizontal expansion, are fundamentally unsustainable under this scale of demand. Urban sprawl consumes valuable agricultural land, increases infrastructure length, and accelerates environmental degradation. From an engineering standpoint, sprawling cities are inefficient. Roads, pipelines, power lines, and drainage systems must cover vast distances, increasing construction costs, material consumption, and long-term maintenance burdens. Energy losses across extended networks further reduce system efficiency. Environmental consequences are severe. Large impervious surfaces disrupt natural drainage patterns, increase runoff, and intensify urban flooding. Heat island effects grow stronger, placing additional strain on cooling systems and energy infrastructure. Social and economic impacts are equally concerning. Longer commute times increase fuel consumption, reduce productivity, and lower quality of life. Infrastructure costs rise while accessibility becomes uneven, creating vulnerable and fragmented urban environments. As climate change intensifies extreme weather events, sprawling cities become more exposed and less resilient. Existing systems were never designed to handle such pressures. Continuing this model will result in cities that are expensive to operate, environmentally fragile, and energy intensive. To meet future demands, engineers must fundamentally rethink urban forms, shifting from outward expansion to vertical, compact, and integrated development. Introducing the vertical city, more than tall buildings, a philosophy of integrated living. A vertical city is not defined merely by height. It represents a comprehensive philosophy of integrated urban living. Unlike conventional skyscrapers that serve single functions, vertical cities combine housing, offices, healthcare, education, retail, and recreation within interconnected vertical zones. This integration dramatically reduces transportation demand. When daily activities occur within close vertical proximity, dependence on long-distance travel decreases, lowering traffic congestion, fuel consumption, and emissions. Structurally, vertical cities rely on advanced engineering systems such as megacolumns, core outrigger frameworks, composite materials, and vibration control technologies. These systems ensure safety, stability, and comfort under extreme loading conditions. Equally critical is the underground dimension. Below ground levels house metro systems, utility corridors, energy storage facilities, logistics networks, and waste processing units. Separating these functions improves safety, operational efficiency, and urban organization. For civil engineers, vertical cities require holistic planning and interdisciplinary coordination. Structural, geotechnical, environmental, and energy systems must be designed together, not independently. The vertical city transforms urban development into an engineered ecosystem capable of supporting high population density while maintaining livability, efficiency, and long-term sustainability. Why geothermal is the key to unlocking true self-sufficiency and minimal footprint. Energy sustainability is the foundation of any vertical city, and geothermal energy offers a uniquely effective solution. Unlike solar and wind power, geothermal systems provide continuous, reliable baseload energy, independent of weather conditions or daylight availability. By drilling deep boreholes or integrating geothermal heat exchangers into foundation piles, skyscrapers can harness Earth's internal heat for heating, cooling, and power generation. This makes geothermal energy especially compatible with high-rise construction. From a civil engineering perspective, geothermal integration enhances efficiency by enabling dual-purpose foundations serving both structural and energy functions. This reduces land use, material requirements, and overall environmental impact. Geothermal systems significantly lower operational carbon emissions and reduce reliance on centralized power grids. When combined with thermal energy storage, smart controls, and district heating networks, vertical cities can approach net zero or net positive energy performance. Most importantly, geothermal energy allows cities to generate power directly beneath their footprint. This eliminates the need for expansive power plants and long transmission corridors, preserving land and improving resilience. For future metropolises, geothermal energy is not simply an alternative, it is the engineering backbone that enables true self-sufficiency and sustainable vertical urbanization. Harnessing Earth's power. Geothermal foundations. At the core of every vertical city lies its foundation, and in future metropolises, foundations are no longer passive structural elements. They are active energy-generating systems. Geothermal foundations represent a transformative shift in civil engineering, where deep structural systems are designed to simultaneously support massive vertical loads and harness Earth's internal heat. Geothermal energy originates from radioactive decay and residual heat within the Earth's crust. By accessing this stable thermal reservoir, cities can achieve continuous, low-carbon energy generation directly beneath their footprint. For vertical cities, this is especially critical as high-rise structures demand enormous and constant energy for heating, cooling, ventilation, and vertical transportation. From an engineering standpoint, geothermal foundations integrate deep boreholes, geothermal piles, and heat exchanger loops within structural foundation systems. These foundations often extend several hundred meters below ground level, placing them in ideal thermal zones with minimal temperature fluctuation. Unlike conventional energy systems that require large surface areas, geothermal foundations use subsurface space, preserving valuable land for urban and ecological use. This makes them uniquely suited for dense urban environments where space efficiency is paramount. Beyond energy production, geothermal foundations improve thermal stability within buildings, reduce peak energy loads, and enhance long-term operational resilience. When combined with smart energy management systems, they allow vertical cities to function with minimal dependence on external power grids. For civil engineers, geothermal foundations demand interdisciplinary expertise blending geotechnical engineering, structural design, thermal analysis, and construction technology. They redefine foundations as multifunctional infrastructure, forming the energetic backbone of future vertical cities. Deep dive into advanced geothermal drilling techniques and enhanced geothermal systems (EGS) for urban environments. Implementing geothermal systems in dense urban environments requires advanced drilling technologies and innovative engineering solutions. Traditional geothermal wells, often used in rural or volcanic regions, are not always feasible in cities. This is where advanced geothermal drilling techniques and enhanced geothermal systems (EGS) play a critical role. Modern geothermal drilling uses directional and horizontal drilling, similar to oil and gas exploration, allowing engineers to reach deeper and hotter rock formations while avoiding surface obstacles such as existing buildings and underground utilities. These techniques minimize surface disruption, an essential requirement for urban construction. Enhanced geothermal systems take this concept further. In EGS, engineers artificially stimulate hot, dry rock formations by creating controlled fracture networks deep underground. Water is injected into these fractures, heated by surrounding rock, and then extracted to the surface as thermal energy. This approach allows geothermal energy to be developed almost anywhere, not just in naturally geothermal regions. For vertical cities, EGS enables geothermal integration even beneath megastructures. Deep boreholes, often extending 3 to 5 kilometers, can be drilled beneath foundation systems, turning the subsurface into a permanent heat reservoir. From a civil engineering perspective, EGS requires careful geotechnical analysis, seismic risk assessment, and real-time monitoring to ensure safety and stability. Microseismic monitoring systems track rock behavior during stimulation to prevent unwanted ground movement. These advanced drilling techniques unlock geothermal energy at an urban scale, making it a reliable, scalable solution for future cities. For engineers, mastering EGS technology is essential to delivering sustainable energy solutions within increasingly dense metropolitan environments. Innovative heat exchange networks, how geothermal energy powers heating, cooling, and even vertical farms. Extracting geothermal energy is only part part of the equation. The real engineering innovation lies in heat exchange and distribution networks. In vertical cities, geothermal energy is circulated through sophisticated closed-loop systems that distribute thermal energy efficiently across multiple vertical and underground levels. At the core of these systems are geothermal heat exchangers, typically consisting of fluid-filled pipes embedded in boreholes or foundation piles. These exchangers absorb heat from the ground during winter and reject heat back into the earth during summer, providing year-round thermal regulation. This energy feeds district heating and cooling networks, supplying residential units, offices, hospitals, and commercial spaces with stable indoor temperatures. Compared to conventional VAC systems, geothermal networks drastically reduce energy consumption and peak load demand. One of the most innovative applications is in vertical farming. Controlled agricultural environments require precise temperature and humidity regulation. Geothermal energy provides a stable thermal base, reducing operational costs and enabling food production directly within city structures. From an engineering standpoint, these networks require detailed thermal modeling, hydraulic balancing, and redundancy planning to ensure reliability across large vertical spans. Sensors and smart controls dynamically adjust flow rates based on real-time demand, maximizing efficiency. By integrating geothermal heat exchange networks, vertical cities achieve energy cascading, where waste heat from one system becomes useful input for another. This systemic efficiency transforms geothermal energy into a cornerstone of sustainable urban metabolism. The surprising benefits of geothermal integration beyond energy, water purification, and waste management. Geothermal integration offers benefits that extend far beyond heating and cooling. In vertical cities, geothermal systems can support water purification, wastewater treatment, and waste management, creating highly efficient closed-loop urban systems. Geothermal heat can be used to power thermal water treatment processes, including distillation, desalination, and advanced filtration. Elevated temperatures accelerate chemical reactions and biological treatment processes, improving efficiency and reducing treatment time. In wastewater management, geothermal energy enhances anaerobic digestion and sludge processing. Higher controlled temperatures increase biogas production, reduce pathogen levels, and minimize residual waste volume. This creates an opportunity to recover additional energy from waste streams. Geothermal systems also support thermal separation technologies used in recycling and material recovery. Heat-assisted sorting improves efficiency in waste processing facilities located underground or within vertical infrastructure cores. From a civil engineering perspective, integrating these systems reduces dependency on external utilities, shortens infrastructure networks, and lowers operational costs. Wastewater treatment plants, traditionally land-intensive, can be compactly integrated into subterranean levels of vertical cities. Most importantly, geothermal integration enables circular resource flows, where energy, water, and waste systems operate synergistically. This transforms cities from resource consumers into resource recyclers. For future metropolises, geothermal systems are not just energy solutions, they are multifunctional infrastructure platforms that redefine sustainability at the urban scale. The subterranean symphony, networks beneath our feet. While vertical cities capture attention with their towering skylines, their true functional strength lies beneath the surface. Subterranean infrastructure forms the hidden framework that enables dense urban systems to operate efficiently, safely, and sustainably. In vertical cities, underground space is not an afterthought, it is a strategically engineered dimension. The subsurface environment allows cities to relocate critical infrastructure away from congested surface levels. Transportation corridors, utility networks, energy storage systems, data centers, and logistics facilities can operate underground with reduced interference and improved resilience. This separation of functions enhances operational reliability while freeing surface areas for pedestrians, green spaces, and social interaction. From a civil engineering perspective, underground networks offer significant advantages. Subsurface systems experience lower temperature fluctuations, reduced exposure to weather extremes, and enhanced security. These conditions improve the lifespan and performance of infrastructure components. The term subterranean symphony reflects how multiple underground systems transport, water supply, drainage, power, waste, and communication must work in precise coordination. Any failure in one system can affect the entire urban ecosystem, making integrated design and monitoring essential. Advances in tunneling technologies, digital modeling, and construction automation have made deep urban excavation more feasible than ever before. As cities grow vertically, underground networks provide the counterbalance, supporting massive populations without expanding outward. For future metropolises, the success of vertical cities depends not only on what rises above ground, but on how intelligently engineers design and manage the invisible systems beneath our feet. Beyond basements, exploring multi-layered subterranean networks for transport, utilities, and public spaces, modern underground infrastructure extends far beyond traditional basements and parking levels. In vertical cities, engineers design multi-layered subterranean networks where each depth level serves a distinct function within the urban system. At the upper underground levels, high-capacity metro lines and automated transit corridors move people efficiently across dense urban zones. These systems reduce surface congestion and enable seamless vertical to horizontal mobility. Below transport layers, utility corridors house water supply pipelines, sewage systems, power cables, data lines, and district heating networks in organized, accessible tunnels. Deeper levels are increasingly used for logistics and storage. Automated freight tunnels allow goods to move directly between distribution hubs and buildings without surface traffic. Energy storage systems, including thermal and battery storage, are also placed underground to improve safety and space efficiency. One of the most progressive developments is the integration of underground public spaces. Shopping areas, pedestrian plazas, emergency shelters, and climate-controlled walkways are being designed below ground, enhancing urban usability in extreme weather conditions. From an engineering standpoint, these multi-layered networks require precise spatial planning, structural zoning, and redundancy design. Each level must be accessible for maintenance while remaining isolated from failures in adjacent systems. By extending cities downward in a structured manner, civil engineers unlock enormous spatial potential, transforming underground space into an active and valuable component of future urban life. Engineering challenges, managing seismic activity, water infiltration, and structural integrity in deep urban digs. Constructing deep underground infrastructure in dense urban environments presents some of the most complex challenges in civil engineering. Among the most critical are seismic risk, groundwater control, and long-term structural stability. Seismic activity poses a significant threat to underground systems. Although subterranean structures often perform better than surface buildings during earthquakes, improper design can lead to tunnel deformation, lining cracks, or joint failure. Engineers must conduct detailed seismic hazard assessments and apply flexible design strategies such as segmental linings, shock-absorbing joints, and ground structure interaction modeling. Water infiltration is another major concern. Groundwater pressure increases significantly with depth, and uncontrolled seepage can compromise structural integrity and safety. Engineers employ advanced waterproofing systems, including membrane linings, grouting, and pressurized tunnel boring methods to manage water ingress. Geotechnical variability adds further complexity. Soil and rock conditions can change rapidly with depth, requiring real-time monitoring during excavation. Instrumentation systems track ground movement, pore pressure, and structural response to ensure excavation safety. From a structural standpoint, underground spaces must resist earth pressure, hydrostatic forces, and long-term creep effects. High-performance concrete, corrosion-resistant reinforcement, and continuous inspection systems are essential for durability. Successfully managing these challenges requires interdisciplinary coordination between geotechnical, structural, seismic, and construction engineers, making underground development one of the most technically demanding aspects of vertical city design. Case studies and conceptual designs, visualizing the invisible infrastructure that makes vertical cities thrive. Although much of subterranean infrastructure remains invisible, several real-world projects and conceptual designs demonstrate how underground systems enable high-density urban living. Cities like Singapore, Helsinki, and Tokyo have pioneered extensive underground networks to support transportation, utilities, and public facilities. In Singapore, deep underground utility corridors consolidate power, water, and communication systems into shared tunnels, reducing surface disruption and improving maintenance efficiency. Helsinki's underground master plan integrates energy storage, data centers, and public facilities beneath the city, optimizing land use while enhancing resilience. Conceptual vertical city designs take this approach even further. Multi-level underground zones are mapped digitally using building information modeling (BIM) and digital twin technologies, allowing engineers to visualize interactions between systems before construction begins. These models reveal how transport tunnels intersect with utility corridors, energy systems, and structural foundations, ensuring conflicts are resolved during the design phase rather than on site. Advanced visualization tools also support long-term planning, allowing future expansions without compromising existing infrastructure. From a civil engineering perspective, these case studies highlight the importance of systems thinking. Underground infrastructure must be planned decades in advance, with flexibility for technological upgrades and population growth. By visualizing and engineering the invisible, civil engineers transform underground space into a strategic asset, one that allows vertical cities to function efficiently, safely, and sustainably. Skyscraper innovations. Living above the clouds, skyscrapers are no longer defined solely by height or architectural expression. In vertical cities, skyscrapers become self-contained urban systems engineered to support living, working, food production, and energy efficiency at extreme elevations. These structures represent the most advanced convergence of structural engineering, material science, environmental design, and digital technology. At extreme heights, buildings are subjected to intense wind loads, seismic forces, thermal gradients, and long-term material fatigue. Modern skyscraper design therefore focuses on performance rather than form alone. Aerodynamic shaping, tuned mass dampers, and adaptive structural systems are now essential components of high-rise engineering. Beyond structural performance, skyscrapers in vertical cities must function as habitable ecosystems. Water recycling, waste processing, energy generation, and climate control are integrated directly into the building envelope. Vertical transportation systems, high-speed elevators, multi-directional lift technologies, and autonomous logistics shafts enable efficient movement across hundreds of meters. Skyscrapers also play a critical role in urban sustainability. By concentrating population and infrastructure vertically, they reduce land consumption and allow surrounding areas to remain open for ecological balance and climate adaptation. For civil engineers, these innovations redefine skyscrapers from isolated landmarks into multifunctional urban infrastructure. Living above the clouds is no longer a luxury concept. It is a necessary response to the spatial, environmental, and social demands of future megacities. Material science breakthroughs, lightweight, super strong composites, and self-healing concretes for extreme heights. The future of skyscraper construction depends heavily on breakthroughs in material science. As buildings rise higher, traditional materials face limitations in weight, durability, and long-term performance. To overcome these challenges, engineers are adopting advanced composites and next-generation concrete technologies. High-performance composite materials such as carbon fiber reinforced polymers and hybrid steel composite systems offer exceptional strength-to-weight ratios. By reducing structural self-weight, these materials lower foundation loads, improve seismic performance, and allow greater design flexibility at extreme heights. Self-healing concrete represents another major innovation. This material incorporates microcapsules or bacteria that activate when cracks form, automatically sealing them and preventing moisture ingress. For skyscrapers, where maintenance access is difficult and expensive, self-healing concrete significantly extends service life and reduces life cycle costs. Ultra-high-performance concrete UHPC is also gaining prominence. With compressive strengths far exceeding conventional concrete and improved ductility, UHPC enables slimmer structural elements without compromising safety. This allows more usable floor space while maintaining structural integrity. From a civil engineering perspective, these materials require new design methodologies, testing standards, and construction techniques. Engineers must understand long-term behavior, compatibility, and sustainability impacts. By combining lightweight composites with intelligent concrete systems, future skyscrapers become stronger, more resilient, and more efficient, making extreme vertical construction both feasible and sustainable. Vertical farms and biophilic design, integrating nature and food production directly into skyscraper facades. As cities grow denser, access to green space and fresh food becomes increasingly limited. Vertical cities address this challenge by integrating vertical farms and biophilic design directly into skyscraper structures. Vertical farms utilize stacked hydroponic, aeroponic, or aquaponic systems to grow food within controlled environments. By embedding these systems into building facades and interior zones, skyscrapers can produce fresh vegetables year-round with minimal land and water use. From an engineering standpoint, integrating vertical farms requires careful structural and environmental planning. Additional loads from soil-free growing systems, water circulation, and lighting must be accounted for in design. Climate control systems must maintain precise temperature, humidity, and airflow conditions. Biophilic design goes beyond food production. Green walls, sky gardens, and planted terraces improve air quality, reduce heat gain, and enhance occupant well-being. Vegetation also acts as a natural shading system, lowering cooling demands. Civil engineers collaborate closely with architects and environmental engineers to ensure these systems are structurally safe, energy efficient, and maintainable. Drainage, waterproofing, and root protection systems are critical to prevent long-term damage. By integrating nature into skyscrapers, vertical cities create healthier living environments while reducing food transportation emissions. These buildings become productive landscapes, merging infrastructure and ecology into a single vertical framework. Smart city integration, AI-powered resource management, autonomous transportation, and hyperconnectivity within the vertical domain. Skyscrapers in vertical cities operate as intelligent systems, enabled by smart city technologies and advanced digital infrastructure. Artificial intelligence plays a central role in managing energy, water, waste, and mobility within these complex vertical environments. AI-driven building management systems analyze real-time data from thousands of sensors to optimize energy consumption, thermal comfort, and lighting. Geothermal energy, solar input, and storage systems are dynamically balanced to reduce waste and peak loads. Autonomous transportation systems further enhance efficiency. Smart elevators with destination control reduce waiting times and energy use, while autonomous freight lifts move goods without human intervention. In some concepts, vertical and horizontal mobility networks are integrated seamlessly. Hyperconnectivity ensures continuous communication between building systems, city infrastructure, and occupants. Digital twins virtual replicas of skyscrapers allow engineers to monitor performance, predict failures, and optimize maintenance strategies. From a civil engineering perspective, integrating smart systems requires robust data infrastructure, cybersecurity planning, and fail-safe design. Systems must remain operational even during power outages or emergencies. By embedding intelligence into skyscrapers, vertical cities achieve unprecedented levels of efficiency, resilience, and adaptability. These structures are not just buildings, they are living, learning systems, continuously evolving to meet urban demands. The future is now, pushing the boundaries of urban living. Vertical cities are no longer speculative concepts confined to architectural renderings. Advances in construction technology, energy systems, and digital infrastructure have brought these ideas firmly into the realm of practical engineering. What once seemed futuristic is rapidly becoming a necessary response to real-world urban pressures. As land scarcity intensifies and infrastructure costs rise, vertical cities offer a scalable solution capable of accommodating population growth without expanding city footprints. These developments allow engineers to rethink how space, energy, and resources are allocated within urban systems. From a civil engineering perspective, the shift toward vertical cities signals a fundamental change in urban development philosophy. Infrastructure is no longer distributed horizontally across vast areas, but concentrated vertically, improving efficiency and resilience. Integrated systems reduce redundancy, minimize energy losses, and simplify long-term maintenance. Technological readiness is also accelerating adoption. High-performance materials, geothermal energy, advanced tunneling, and smart control systems have matured enough to support complex vertical environments. Digital design tools enable precise planning, simulation, and life cycle analysis before construction even begins. Most importantly, vertical cities represent an opportunity to redefine quality of life in dense urban settings. By combining compact living with access to green spaces, efficient transport, and clean energy, these cities challenge the assumption that density must come at the cost of livability. The future of urban living is not decades away, it is unfolding now. Civil engineers stand at the forefront of this transformation, responsible for turning bold concepts into safe, functional, and sustainable realities. Economic and social implications, affordability, community building, and changing urban dynamics in vertical cities. One of the most critical questions surrounding vertical cities is their economic and social impact. While high-rise developments are often associated with luxury, vertical cities aim to address affordability and inclusivity through efficient land use and shared infrastructure. From an economic standpoint, concentrating infrastructure vertically reduces the cost per capita of utilities, transportation, and public services. Shared energy systems, centralized water treatment, and integrated waste management lower operational expenses over the building life cycle. These efficiencies can translate into more affordable housing when properly regulated. Socially, vertical cities reshape community dynamics. Mixed-use vertical zones bring residents, workplaces, schools, healthcare, and recreation into close proximity. This fosters stronger social interaction and reduces time lost to commuting, improving work-life balance. However, engineering design must actively support community building. Public terraces, shared green spaces, vertical plazas, and communal facilities are essential to prevent isolation within tall structures. Circulation systems must be intuitive and accessible, promoting interaction rather than segregation. From a civil engineering perspective, equitable design also involves accessibility, safety, and resilience. Vertical cities must serve diverse populations, including elderly residents and people with disabilities, through redundant systems and inclusive planning. If designed thoughtfully, vertical cities can reduce urban inequality by providing affordable, connected, and sustainable living environments. The challenge lies in ensuring that engineering innovation aligns with social responsibility and long-term economic viability. Regulatory hurdles, and public perception, paving the way for these ambitious urban developments. Despite their technical feasibility, vertical cities face significant regulatory and societal challenges. Existing building codes, zoning laws, and urban planning regulations were developed for conventional city layouts and often fail to accommodate ultra-dense, multi-layered development. From a regulatory standpoint, issues such as building height limits, underground property rights, fire safety, evacuation strategies, and seismic performance must be re-evaluated. Underground construction, in particular, raises legal questions regarding land ownership and utility corridors. Civil engineers play a key role in addressing these challenges by providing data-driven evidence of safety, performance, and resilience. Advanced simulations, full-scale testing, and digital twins help regulators understand how vertical cities function under normal and extreme conditions. Public perception is another major hurdle. Many people associate high-density living with congestion, reduced quality of life, and social isolation. Overcoming this perception requires transparent communication and demonstration of tangible benefits such as reduced emissions, improved mobility, and access to green spaces. Pilot projects and phased development strategies can build public trust. By demonstrating successful, livable vertical environments, engineers and planners can shift perception from skepticism to acceptance. Ultimately, regulatory frameworks must evolve alongside engineering capabilities. Collaboration between engineers, policymakers, and communities is essential to unlock the full potential of vertical cities. A glimpse into the first pilot vertical cities breaking ground by 2030 and their potential global impact. By 2030, the first generation of pilot vertical cities is expected to move from concept to construction. Several countries are already investing in large-scale mixed-use vertical developments integrated with renewable energy, underground infrastructure, and smart city systems. In Asia and the Middle East, land scarcity and rapid urbanization are driving early adoption. These pilot projects focus on energy self-sufficiency, automated transportation, and deep underground utility networks. In Europe, vertical city concepts emphasize climate resilience, carbon neutrality, and adaptive reuse of urban space. From a global perspective, these pilots serve as living laboratories. Engineers can study structural performance, energy efficiency, social behavior, and long-term maintenance in real-world conditions. Lessons learned will inform design standards and best practices worldwide. The global impact of successful vertical cities could be profound. Reduced land consumption protects ecosystems and agricultural zones. Compact infrastructure lowers emissions and energy demand. Cities become more resilient to climate extremes and population growth. For civil engineers, these pilot projects represent a defining moment. The knowledge gained will shape urban development for generations. Vertical cities are not just ambitious ideas, they are the blueprint for how humanity will live, build, and thrive in the decades ahead. As we look toward the future, one thing becomes clear: civil engineering is no longer just about building structures. It's about shaping civilization itself. Vertical cities powered by geothermal energy and supported by intelligent underground networks are not distant dreams. They are realistic, engineered responses to the challenges of population growth, climate change, and limited resources. From deep geothermal foundations to smart skyscrapers and subterranean infrastructure, every concept we explored today places civil engineers at the center of humanity's future. The decisions we make today about materials, energy, design, and systems integration will define how billions of people live tomorrow. At Civil Engineering Edge, our mission is to explore these cutting-edge ideas, break down complex engineering concepts, and prepare the next generation of engineers to lead this transformation. If you found value in this deep dive, like the video, subscribe to the channel, and stay connected, because the future of cities is vertical, intelligent, and engineered by us. See you in the next one.